Okay, we are on slide 36. I'm going to write that here. Slide, and it will say 1836. So chapter 18, slide 36, but we are on section 18.7. So in the previous slide we saw the same reaction. You have an electron donating group and an incoming electrophile. So if you look at the previous video, you will see that the toluene molecule is going to react faster than the benzene ring, the plain benzene ring, because there is an electron donating group attached to the ring. So also I said that in the ring there are 3 unique positions. You have the ortho, you have the meta, and then you have the para, right? So if you have an electron donating group, specifically the methyl group, what are the 3 products possible? So the nitro group could be installed at the ortho position, the meta, or para. At the ortho, meta, or para. Positions. So there are 3 possible products, but will you get 3 possible? Will you get all 3 products, or do you have more of one and less of the other 2, or do you have more of any 2 and less of the third one? So let's check that out. So if you have a methyl group, all right, and remember this is an electron donating group, here are the structures of the 3 products. Ortho nitrotoluene, that's the name of this product, ortho nitrotoluene, meta nitrotoluene, para nitrotoluene. So do we get equal amounts, like 33% of each? Not really. We get 63% of the ortho. One, because you remember, and you see it here too, you have 2 ortho positions and only 1 para position. You see that? So you get 66% of this about, and 33% of the para. So that makes sense. But methyl group says, no, you're not going into the meta rooms. Remember? The guest is not allowed in the meta room, only in the 2 ortho rooms and the para room, if you think about it. Now, why is that so? So there's an explanation for why the electron donating groups, also called as, now we have another name for these, sorry, there's a little glare there, Donating groups, also called as the activating groups. Activating groups. So why is that? So this is how we are going to prove or give an explanation for why we have more of the ortho and more of the para and not so much of the meta. All right. So how do we start these off? I'm going to show you how to start off these sigma complex intermediates. Okay, so I'm going to show you, let me see if it's showing up on the screen. Yes. I have the methyl group. Now your nitro group, remember that is your incoming nucleophile, and also you need to know how to draw these electrophiles, the Lewis structure of these electrophiles. So that's something that you have to be practicing, showing all the lone pairs at least on the first one. Now we are going to send the electrophile to the ortho position. All right, so I'm going to take this, and then I have to move one of these around. Okay, now to give an explanation for why this activating group gives more of the ortho product and the para product and not so much the meta, you don't have to really keep this opened up. You see how they've closed it up, because we are not going to be talking about that part when we get to this box region. Now let's look at the 3 resonance structures that they've drawn. You should be able to draw these, but if you look closely, the positive charge is at this position. See that? And then in the next structure, the positive charge is here, and then here. All right. So you're able to draw 3 resonance structures. Look at this structure. Okay, this is the guy with the money. He's electron donating. What does he do? He pumps in electrons to the ring. How is he pumping in electrons? The first hit is that carbon. Okay. Now you see that they have shaded this resonance structure. That's because the electron donating group is right adjacent to that carbon with a positive charge. So this resonance structure is stabilized. Okay, by the electron donating group pumping in electrons to that carbon that has the positive charge. So it kind of tries to neutralize it, and therefore this resonance structure is, I'm going to say, further stabilized by the presence of the electron withdrawing group. I'm sorry, electron donating group. All right, so you have 3 structures, but one is extra stable. So you might have something like 50% of this, 25% of that, and 25% of that, if you remember resonance contributors from chapter 2, I suppose. Okay, so that's why ortho substitution is favored. Move this in, is favored. Let's look at what happens at the meta position. Okay, so let's learn how to draw these, because you should be able to draw these, start these off. I'm going to draw it like before, okay, fixing the double bonds. Now you want the same nitro group, but to attack the meta position. So for the ortho position, you use this pair, all right? For the meta, we'll use the one below, that's all. Not rocket science, right? So go there, then move that, see that? And then it opens up like that. All right, you may want to practice drawing these. And your positive charge is here for the first resonance structure. And again, meta attack. And then move this down. You have a positive charge here. And the third one has a positive charge here. So the positive charges are at the ortho positions and then one at the para position, okay? But you do not have a positive charge at the adjacent carbon. You see that? So, summarizing, you have 3 resonance structures, but the 3 resonance structures are equally stable. Okay, so there's not one position that is favored over the other. So do not worry about where these positive charges are. What you have to look at is this. When the nitro group is connected to the ortho position, you have 3 resonance structures, but extra stability to the first structure here. So when you compare this with the resonance structures you get when the nitro group is in the meta position, you have resonance structures like normal, but the extra stability is missing. Okay, so I'm going to say here extra stability for one or more structures is missing. Okay, so if you have 2 jobs to pick, one, a job like that is, gives you the normal stability economically, whereas you have another job where, for a part of the job or an aspect of the job, there's extra economic stability. You see that? I'm trying to come up with an analogy here. So this is preferred. So I would prefer this job over that job. So the nitro group, when you have CH3, because it has this cushion here, it prefers going into the ortho position, and it's like, okay, if I can avoid this, I'm going to avoid this, and they will not go into the meta position. The last one is the para position, and it's similar to the first case, the ortho attack. So now you've used up the first 3 bonds for drawing the first 2 sets of resonance structures. So you see where I'm going now. I'm going to use the I'm going to use this. But I'm going to position my nitro group here, and I'm going to move the positive charge here. See that? Okay. So don't be confused by that. I'm still using the same pi bond, but I'm positioning the nitro group here with a positive charge there. Okay, so you can pick, you can use that and put the nitro group there and a positive charge there, or just to make it convenient for us, use the same here, but put the nitro group in the ortho position and the positive charge at the next carbon here. Now, as you draw the resonance structures, you see that the next time your positive charge is adjacent to the electron donating group. Okay, so I'm going to write here further stabilization provided let me provided. Okay, that's better. And then you have the third structure where the positive charge is there. All right, so you have three, but this has more stabilization than either this or that. So para substitution is also favored. Para all right, okay, I'm gonna pause here.